Thanks again, Sally. Thanks, Steve, for inviting me. I'm very pleased to be in front of a very varied audience that I think that comes both from the application side as well as the data analytics. Because I do believe that dealing with a large data set of many different kinds, but in particular data that are collected by physical sensors, they do need the cooperation between many sides of sciences. Needs the domain application person that understand the physics or whatever the phenomenon that is beyond the data that we collect, as well the data analytics one. In particular, I'm interested in seismology, and in the past few years, there have been a very fast development of seismic sensors. And that has to do both with the cost, with power consumption, with potential of being able to deploy it in very varied configurations. And that, I believe, it is making a huge difference in seismology, and in particular when we just listen to what Earth has to tell us, not when we stimulate the Earth with active sources. I should say that I do come from the active source side of seismic surveying. That is my day job, just to tell you the kind of the level of effort. I have about 15, 17 PhD students, and at every time I had in the past few years, 1 or 2 students working on passive data. But I do think that that may increase because there are indeed a lot of opportunities there. I'm going to talk mostly about using dense sensors arrays to monitor subsurface processes. And all the data and all the results that I'm going to show you is really produced by Shor Derrida, that was a student of mine until a few months ago. Now he moved to Hefei, China, to be a junior faculty at USTC. And what is beyond the results that are more the speculation and the abstract thinking that is probably not necessarily correct, that is due to me, and I'm the one to blame. But the good results are Shor's, not mine. So what active seismic surveying is a big data industry. I don't think that there are many questions about that, though you may see there that the big data is in lowercase. So indeed, we do collect a large amount of data, like by modern seismic boards, like the one on the right, that they pull 10, 15 streamers with a lot of sensors. The most modern seismic boards, they have about 100,000 sensors collecting at a rate of 2 milliseconds per sample. If you make simple math, it's about 20 terabytes of data a day. And since they are expensive boards, they go on 24 hours a day. And there are about 90 of them in the world operational, not of the top ones. Well, the number that I gave you is the top one, but this is a arm race among the geophysical contractors, so they will upgrade to that kind of numbers pretty soon, and the top one will get larger numbers. That has to be expected. And that is for marine surveying. For land surveying is about collecting the same amount of data as for marine, so you need to put a factor of 2. So that is active seismic surveying. Though in the past 10 years, as sensors have become cheaper, companies have been deploying large dense arrays of permanent sensors. So far, they have been justified in terms of cost based on repeated active surveying. So these 2 sensors array that are showed here on the slide, they are in the North Sea, and they really pay for themselves by every 3-6 months having an active surveying and understanding how the reservoir is changing, and then optimizing the production. But they have a regional amount of number of sensors, again, 10,000 from the one on the left, 16,000 for the one on the right, that is fiber optic sensing. And since they are there, we ask companies to say, what about if you collect data not just when you're shooting, but when there is nothing going on. And that is somewhat what started our projects there. And I'm going to talk about how to use that kind of passive data to monitor subsurface processes. This can be applied for conventional oil and gas reservoir, but can also apply for unconventional uses like monitoring CO2 sequestration project. And indeed, GSAP was very generous a couple of years ago to support some of the work that I am going to show. Another very important application of passive seismic sensors is the one of microseismic. In particular, that I think that will have a huge impact when it's in conjunction with hydraulic fracturing, fracking. That's probably, you ever heard of that term, for unconventional oil and gas reservoirs. Sometimes they're called shale gas. And not only can improve economics, but can actually decrease the number of wells, decrease the numbers of frac jobs, and so we have much less of an impact on the environment, less use of fresh water, less production of wastewater. Now, that's it from the industry side. There are potential great application on the earthquake seismology side. At the end, I have the slides about that. I just noticed that my colleague Greg Berosa is sitting there in the corner, and he has been leading those efforts. There is a potential of a real-time earthquake detection, and if you do be able to detect an earthquake that is happening in real time, you can shut off a lot of infrastructure, save lives, and save infrastructure. That is a huge impact. As well, a more scientific one, you can start to, using big data analysis, try to see the kind of earthquakes that they have been called in that community tremors that are not apparent from kind of smaller data conventional seismic application, and that does give us more insights on earthquake mechanism and potentially understanding and maybe even predicting earthquakes. So that's the application. Let me go instead to what the main topic of my talk that has to do with passive seismic interferometry for reservoir scale imaging. And it's really made by two steps. The first one is transforming the noise that is always going on in the Earth to what we call virtual sources. So what look like incoherent noise, now we transform in coherent data in which then we can transform in estimation of parameters, in particular, for example, seismic velocities. So the first part has a statistical data analysis component that is start to bring the big data with capital letters. In seismic imaging, that is the next step, we do use statistics, and maybe we abuse it sometime, but it really is driven by understanding of the physics and is using the understanding of the physics what's happening. Now, in the first step, and that is what I'm mostly going to explain today, the statistical data analysis instead is somewhat new. We are trying using statistics, particular spatial correlation, to extract coherent data. In more even general terms, as you will see, really the first step is, in some sense, is a discovery, is a data discovery. That gets again closer to the big data problems. As you will see, actually, we first took some blind alleys because we didn't look at the data or we didn't listen to the data carefully. We used our conventional blind sides, and we misinterpreted what we were seeing. So there is a lot of data discovery, if you want, of sciences there. Then the next step is what we do in our day job, is going from a coherent experiment, a virtual experiment, to estimation of parameters using some kind of large-scale inverse theory, and that's somewhat, I think, it is less relevant really to the big data and to today discussion. Now, I will run very quickly about the history of passive seismic interferometry, because I think that is quite interesting how sometimes science goes through detours. It was actually first hypothesized by John Claerbout here at Stanford in exploration seismology in the 60s. We never had the sensor to do anything useful with it, and actually the helioseismologists did something useful at NASA and at Stanford, starting, I believe, in the 80s and the 90s. And then, I have to say, really hurting our pride of reflection seismologists, the global seismologists did something useful using their arrays. And they did, this is shown in 2005, the first examples of tomography using interferometry. And here is a little of the history instead of doing dense array industry ones. And we saw it coming. We tried. We got data from companies to try to do it. But as I said, the blind sides were, I mean, our own fault. We failed. We were basically looking at the wrong wave modes. We were looking for what we used every day, that are body waves and reflections, while instead most of the energy was in the surface waves. We looked at the wrong frequencies. We looked at the 5 to 25, 40, 100 hertz that we are accustomed to use. Instead, a lot of the signal was in the lower frequency. So the good news is the student that did that ended up graduating. His thesis was inspired by interferometry, but was not about really interferometry. And then I got assured that he is a very perseverant, sometimes stubborn student, and he said, I want to make it work. And he came here, we looked at the data, same data, some different data, and indeed he produced in around 2010 the first reservoir scale images from seismic interferometry. Now, where is the data discovery? I'm showing the next few movies. This is the frequency band that we are used to look at. And if you look at that frequency band, you have a lot of noise coming from the platforms. This is a producing field. And naturally, some noise coming from nearby fields. These are active surveys that the contaminate arrive there 30, 40 kilometers away, but they do contaminate our data. Even if we go at lower frequency, we're still getting a lot of platform noise. We needed to go to even lower frequency that we are not accustomed to look at to start to have pure noise, or noise that actually we could use, at least in a relatively simple way with simple correlation. So this is lower frequency, and this is even lower frequencies. So frequency was important. Understanding what the Earth was telling us was important, and also the wave modes. The next few slides depict for the non-seismologists what are surface waves. In this case, are actually interface waves, interface between the ocean bottom and the water column. There are main two wave modes. On Earth, they are called the Rayleigh's waves. On ocean bottom, they are called shorty waves and love waves. And I have a few movies here to give you a sense that actually, if you live in the Bay Area or in area like we have, a few miles away from San Andreas, these are the waves that you need to fear. These are the waves that first they shook you up and down pretty badly. These are the shorty waves. And the next one are the love waves, that they are the one that shake you left to right in your building and may make the real damage. In this case, they are actually useful to basically see something in the subsurface that otherwise we cannot see. Now, the statistical tool that we use is very basic. It's cross-correlation, it's spatial cross-correlation between the sensors. In seismology, we believe in spatial heterogeneities and in stationarity with time, at least within the time span of experiment. So we try to not to be sophisticated in the spatial correlation. You can have a higher order correlations, and people have tried, but we believe basically in simple first order correlations. But we do believe in redundancy of time, and that will actually help us to extract signal out of the noise. So we do spatial correlation between every sensors, every other sensor, and from there we can basically create a virtual experiment that give us as if we had a source at that point, and that's for every point in on the array. So that fact that we can do for every point in the array is the one that allows us to estimate the heterogeneities in the subsurface. And this is one of those virtual sources, and as the movie goes on, that virtual sources will keep moving in different locations, because you can indeed do that for every location. Now, we use that also though the stationarity, at least within the few hours of the subsurface to average over time. So this is the result between two sources, two receivers, is a correlation now average over time. And you see that from basically no signal, a lot of noise, slowly we converge to something that is actually signal. Short did a very sophisticated statistical analysis there, and depends on the field condition, we can get good data every 6 hours, 24 hours. And that allows now to monitor changes in the subsurface with the time scales in the 6 hours, 24 hours. Nothing that with active survey will be economical. We cannot go back and shoot another active service within that time frame. But sometimes important phenomena happen with that time frame in the subsurface. That was just two sensors. This is a set of sensors, same things. As you average longer and longer, now out of the noise comes out the signal. And this is one of those virtual sources. This just introduces the concept of the distance between source and the receiver that we call offset, just to compare the data collected or synthesized from the noise to the active data. The left is the active data. It's much richer. Those things that we every day use are the reflection body waves. They are there. That's what we were first looking when we looked at this data. But what we have been reliably being able to get are the surface waves that do exist at higher frequency in the active data. But these are the ones collected from the passive data. One thing that you will see here is that different frequency travel at different speed. The lower frequencies tend to come earlier, and indeed that can be done what we call dispersion analysis. This apparent velocity is a function of frequency. But just to tell you that is actually, because we have that phenomena, we can investigate not just the surface, but down in depth. That phenomena of frequency dispersion allows us to have some depth resolution. So these are surface waves, Rayleigh waves in particular, propagating a low frequency on the top and a higher frequency on the bottom. You see the low frequency investigate much deeper than the higher frequency. So that's what allows us basically some depth resolution. So far, I have been really talking about uniform data. From a big data point of view, the statistics, what was somewhat interesting, but really we don't have so far multi-parameter data. In reality, our sensors, they do have multi-component sensing. So you start to be able to actually to do a multi-parameter analysis. Compared to some of what is done on web data is fairly trivial or simple, but we can start to think about, again, as the different components of the seismic sensors. We can, again, interpret them physically in terms of shorty waves and lava waves, as is depicted in this diagram. But you can start to think about doing more sophisticated data analytics on these different sensors. So that is the first move towards more, if you want, big data, at least in the way that I understand it, the way that Jeff was showing the big book about an hour ago. As we will see, also the next step will be actually different physical measurements, and I will mention that in a short while. So now, good news is that we had the active seismic survey to ground truth what we are getting. You know, we tend to be skeptical. It's nice to see nice patterns and nice figures, as Margot pointed out, and claim that reality. But whenever you talk with statistical methods, that is very dangerous. The good news here is those arrays were also collecting active data and give us much more reliable information. And here is a comparison of the different depth slice on the right, obtained from active surveying and pretty sophisticated and expensive, computation-intensive processing and imaging, with frequency slices of the group velocity maps that I was saying, and different frequency tells us about different depth. And of course, the active sensing has much higher resolution, but we do see the similar features from the active sensing and the passive one. So that is a snapshot, is the static images. Our important confirmation was the fact that we can monitor changes over time. And again, here it helped to confirm that the fact that the active sensing was being done every few months for many years in a row, and we had passive data for different years. So this now are differential images, are changes in seismic velocity. And if you look at the scale bars, we're talking about small ones, in the order of 1–2%. But we can sense those 1–2% changes in seismic velocity. And again, the general pattern is confirmed from what was extracted using the active sensing. We can not only find the velocity, but we can also estimate the change of velocity with the direction of propagation. We call that seismic anisotropy. One of the arrays was collected on a field that has strong subsidence. Basically, the bottom of the ocean is going down, is creating differential stresses at near surface, and as such, those differential stresses makes the seismic wave propagate in different directions, different velocity in different directions. On the bottom here is a gradient of the bathymetry of the ocean bottom, and on the right is a display of the seismic anisotropy. The length of the little vectors is the amount of anisotropy, and the direction is the fast velocity of the seismic velocity. And this map here correlates incredibly well with the differential bathymetry on the left, and it correlates with our understanding of the way that this anisotropy is induced by the subsidence in the ocean floor. So we can take different snapshots, looking at differential changes, and also more than just velocity. We look at changes in stress and potential fracturing in the reservoir using passive data. So that is the conclusion of my reservoir scale imaging and monitoring. We can estimate seismic P and S velocity. That tells us a lot about fluid flows and changes of the fluid flow patterns in the subsurface. We can estimate seismic anisotropy. That tells us about stress fields and changes in stress fields and in rock deformation. As I said, it seems that we can extract useful information with a time frequency of 6 hours, 24 hours. And so we can see very fine and temporal scale, at least in the scale of subsurface changes, and can be a continuous monitoring. Today, for the fields that justify for active surveying putting those expensive permanent sensors, the monitoring by passive seismic is justified because the additional cost is minimal, and we may actually extract very useful information for managing the reservoir, avoid environmental disasters, and so that is really something that can be done, at least for the fields that already have permanent sensors. And there are more and more fields that are instrumented with permanent sensors all over the world, both on land and in the ocean. Tomorrow, as the sensor technology keeps improving and gets cheaper and cheaper, I think that it is conceivable that permanent sensor may be deployed just for the sake of passive seismic to monitor in a cost-effective way the changes going on in the subsurface. So that was one, if you want, industry application. I do think that probably in the near future, even one that may have even more impact, and companies are working actively on that, is for really helping to optimize and minimize environmental impact of the shale gas and oil revolution, of fracking and hydrofracking. One of probably of the basic technology that is going to, I believe, a lot of impacts is this idea that you can deploy fiber optics and get sensors out of this fiber optic very densely and not expensively. So this, for seismic, we will have distributed acoustic sensors, or DAS. These fiber optics, they can go up to 30, 40 kilometers long. You can have a sensor every meter. So here again, the big data coming and the kind of density that we like to sample our wave fields. And even more intriguing, they are very flexible. So really, the configuration of your array is somewhat up to your imagination and of the tools that you have to deploy them. So you can be really creative in the way that you deploy those arrays. And the good news is that they're cheap. So companies are considering of basically putting by default when they complete the wells. They put in every single well, and it may be collecting passive data or maybe active data, but really the economics might be there. Now, on the big data and the analytics side, the interesting and intriguing part is that these same fibers will be able to collect temperature data as well as pressure data. So here we have not only multi-component seismic, but different physical data that can be correlated with each other. So there is a lot of data discovery, a lot of interesting statistics, understanding the physical phenomenon and the application that can happen out of this data that is in the future. Now, the last couple of minutes, I would like just to talk about the earthquake application. I have a slide that Greg gave me, I think, for further question. I really will direct to you during the break that is coming. This is his slide. And I think that actually he is using more sophisticated statistics that we have been using, that are one that I will be familiar with some of the data analytics expert, in which basically is trying to deal with the problem that not only there is a large amount of data, but the information is useful if analysis is done in seconds. We are accustomed in seismic imaging using tens of thousands of processors for months to get out an image. You cannot afford to do that if you want an early warning for an earthquake. So they do need to apply much more sophisticated statistics to be able to basically extract and distinguish what is other seismic noise and actually serious earthquake that is hitting you in that area. And finally, I would like to thank mostly all the people in the companies that gave us the data sets that I've showed you the result, that were Schurz thesis, and in particular were BP for one of the data and ConocoPhillips for the other data. I would like again to thank Steve for inviting me and all of you for listening. And I will be very happy to have any question.
Any questions? Come on in. No, come on in. Okay, we've got one back there. Yep.
Hey, Trevor DeMeo with Chevron. Very good presentation. I guess I had a question on one of your last slides where you talked about using these distributed sensors to reduce the number of hydraulic fracturing well jobs and potentially reducing water usage. So just wondering if you could elaborate a little bit on how you propose to do that.
Oh, I should say that I'm not a microseismic expert, as I said. So that is what I see going around me. So all what my comments come from educated layman, if you want. I think that one way of understanding the fracturing process and how that releases hydrocarbons that has been proven, even if not, I would say that is a standard tool, but is very much deployed, is identifying the microseismic events that are generated in correlation with hydrofracking. And that helps you to understand where you may want to frack your formation and where instead it may be not worthwhile to do it because not many hydrocarbon will produce for that particular area with those conditions. So that is where you may save wells, or if you have already your wells where you do have your sensors, you may save some of that hydrofracking that indeed need a lot of fresh water and produce a lot of wastewater, and for which actually there is a problem of induced seismicity, but is another interesting twist between unconventional oil and gas and seismology, for which, again, there is a group of my colleagues that have started just very recently an industrial consortium. And again, Greg will be able to tell you more about that.
Sven Krüger with Baker Hughes. I think very, very interesting presentation. The question I have on this example that you put on the screen here again, you touched on this briefly, and in fact, what we have seen, images that come from the DAS and from geophones are matching surprisingly well. How active are you in this area? How much work have you done related to big data and distributed acoustic sensing?
I not done much of it, but I will very much interested to get into it, because I do think that the kind of expertise that we have in more conventional reflection seismology, dealing with not only large data, but large data coming from dense arrays with many different kinds of shapes and forms, has a lot of relevance, together with better understanding the data analytics with our colleagues in the statistics department or other part of Stanford. I think that's really, you need to put together those two fields that traditionally have not been together to get the best out of that kind of DAS or DAT data. So as I said, I'm very much willing to learn, and I have a lot of bright students that they can really learn.
I've got a technical question. I know nothing about your field, but it looked like you were filtering down to those low frequencies to dodge noise that was contaminating your data set. And a question, when you do that, obviously you're throwing away information. Is the real phenomenon limited to those frequency bands that got through those filters so that you really have sufficient information to work with? Another related question is, obviously there's a real strong signal if they're doing a contaminant from one of these other active things. We've had good luck in other fields of monitoring that signal and then being able to subtract it out, but then basically still get to use that portion of the spectrum that from first blush would appear to be contaminated. You can get rid of the contaminating signal using more sophisticated techniques.
That is an excellent question, but it has many facets to answer. Let me first talking about the low frequency signal. That has to do not only with the noise, but with the nature of the Earth-generated energy. That frequency spectrum is mostly generated actually by ocean waves interfering with each other and pounding on the seafloor, and it actually can go even at lower frequencies. Global seismologists that have seismometers that can go well below the 1 hertz, very much longer period, have been using them. There is not much of that energy at higher frequencies. So there is a part of the kind of what the signal is. However, I have not lost hopes to find body waves in that data. And actually, I should have said, and I'm going to say now, one of the posters that are going to be shown later, I think, this morning, is by a student of mine and a postdoc in the department, looking with a different, slightly different kind of data on land, looking for higher frequency and body waves. So we are still searching for that, because those interrogates the Earth way down kilometers, not just the first few hundred meters. And I have few hypotheses that I would like to test with the data that we have, a potential with additional data, where we eventually find some of body waves created by different mechanisms on in the Earth. And I'm quite familiar. A few decades ago, my background is EE and signal processing, so I think that I'm quite familiar with all the array processing techniques, at least with some of the array processing techniques, that have been used in active seismology as well, because we do have many interfering noise as well. But excellent question.
Are you doing any work to characterize these seismic patterns and relate them to physical phenomena, like your ocean waves has a certain seismic pattern, and then being able to reverse that out of your big seismic jungle there?
In some cases, yes. That is the case of the microseismic, for example. So while we are using the, let's say, quarter 2 hertz, 2 hertz energy propagating in the Earth to estimate parameters in the subsurface, so we don't somewhat care about the physical. I mean, it needs to be there, but the physical phenomenon generating the energy is not our primary objective. The microseismic case is indeed one of the principal objectives is characterizing the physical phenomenon creating the waves that in this case are these small earthquakes that are induced by hydrofracking, the formation to produce oil and gas. And the physical characteristic of that seismic source, it does help actually to understand the stresses in the subsurface and help minimizing wells, minimizing frac jobs, optimizing production. So it can work both ways, depends really on the particular situation. And that, I think, it does illuminate what I think is crucial, at least for physical sensors. You need to have a domain expert that understands the physics or the chemistry or whatever you're looking at, as well as the data analytics people that helps you to have more sophisticated data analytics tools to look at your data.
All right, well, thank you very much.
Thanks again.